Welcome, my dear students, to chapter 12, that is thermodynamics, and we are going to see today topic 12.4 and 12.5. These two topics are going to be very interesting today, but let us see first topic 12.4, that is heat, internal energy, and work. Let us see the definition of heat first of all. Heat is energy transfer between system and surrounding due to difference of temperature. Let me elaborate this. You know that if there is a difference of temperature between a system and a surrounding, let us say if you are talking about a gas in a vessel, then that gas is a system and everything nearby is surrounding, like atmosphere, the vessel itself, the table on which the vessel is kept, all are known as surrounding. So, if there is a temperature difference between system and surrounding, let us say the temperature of system is larger than the surrounding, then obviously the thermal energy will pass from system to surrounding, and vice versa. If the temperature of surrounding is more, then the temperature will travel from surrounding to the system. So this transfer of energy is known as heat. Alright. So this transfer of energy between system and surrounding is known as heat, and it is denoted by Q. Now let us see internal energy. Every bulk system consists of a large number of molecules. The total sum of all the kinetic energies and potential energy is known as internal energy of the system. Let me elaborate this. See, any bulk system, either it is solid, gas, liquid, whatever it is having large number of molecules, and all of these molecules are having some sort of kinetic energy. This kinetic energy can be due to the translation motion, or can be due to the rotational motion, or can be due to the vibrational motion of the molecules, or it can be combination of any of two or three even, right? So that all kinetic energies and the potential energy between them, see, here the molecules are continuously moving, right? And they are having some sort of attractive force and repulsive force and so on. So that's why there will be some potential energy as well. So again, the total sum of all the kinetic energies and the potential energies is known as internal energy, and that is denoted by U. Now let us see the definition of work. Work is energy transfer to the system or from the system by the means of force, and that is denoted by W. Let me explain this. See, when we are applying force on a system and the system is moving, let us say in our case a gas is contained in a piston cylinder system and we are applying force on the piston, so gas is being compressed. So here we are applying force on the gas. Here gas is the system. So here we are applying force on the system and the system is getting compressed. That means there is a displacement, and by the product of this force and displacement we can calculate the work done on the system, right? At the same time, the work is done by some sort of energy. We have applied some mechanical energy to the system, and that's why the work is done. So the amount of energy transferred to the system is the work. It is the work done on the system. Alright. So this was about heat, internal energy and work. There is a relation between heat, internal energy and work that we are going to see later. But before that, first let us understand some important points about internal energy. Here is MP about internal energy. Internal energy U is a macroscopic quantity. We have studied what is microscopic and macroscopic. So here U is a macroscopic quantity. As well as U is thermodynamic state variable like P, V and T, pressure, volume and temperature. See, pressure, volume and temperature, they are thermodynamic state variables. The same way U is also thermodynamic state variable. Means all of these four physical quantities are deciding the thermodynamic state of the system. See, I am not talking about the solid, liquid, gas state. I am talking about the whole thermodynamic state. It includes information about pressure, volume, temperature, internal energy and everything. So that thermodynamic state is decided by PVT as well as U. Here you should also remember that heat and work are not thermodynamic state variables. Students, heat and work are not thermodynamic state variables. See, the interesting part is that heat and work can change pressure, volume, temperature and internal energy of the system, but still heat and work are not thermodynamic state variable. So we can say that heat and work can change the thermodynamic state, but they are not the thermodynamic state variables. Who are thermodynamic state variables? Pressure, volume, temperature and internal energy of the system is thermodynamic state variable. Now, as we already discussed that in gas molecules, they can have 1. Translational kinetic energy, 2. Rotational kinetic energy and 3. Vibrational kinetic energy, as well as 4. Potential energy due to intermolecular forces. So, when we talk about internal energy U, then this internal energy U is sum of all of these 4 energies, means it is sum of 1, 2, 3 and 4. So, again the internal energy of a system is sum of all the kinetic energies and potential energy of the molecules. Now, here is an important contradiction, I would say. See, this is a container having some gas inside. Okay, these are all the gas molecules, and obviously this gas molecule will be having some translation motion, rotational motion, and vibration motion, and they will be also having some potential energy and so on. So, all the kinetic energy and the potential energy, the sum of all the kinetic energy and potential energy is U. That means it is the internal energy that we already know. But now suppose if this container is moving with velocity v, so this whole container will have some kinetic energy, let us say k dash, right? Here I am not taking any mass of the container. Assume that the container is massless. Okay, the mass whatever we are considering is of the gas. Alright, so when I am saying that the container is moving with a velocity v, that means the whole gas is moving with velocity v, and so the whole gas is having this kinetic energy k dash. Okay, now this gas will have some mass, and due to that mass it will have a force mg, and due to that mg it will have a potential energy, gravitational potential energy. So this whole gas is having a potential energy, let us say p dash. Now we already know that the sum of total kinetic energy and potential energy of the gas is known as mechanical energy E, right? This is known as mechanical energy E. But mind well, this mechanical energy cannot be considered as the internal energy U. Okay, the total sum of kinetic energy of the whole gas and potential energy of the whole gas is mechanical energy, but it is not the internal energy. Internal energy is the sum of kinetic energy of the molecules and potential energy between the molecules, right? So this is a very big difference between the internal energy and the mechanical energy. Now here we are going to see the relation between internal energy, work and heat, right? For that, first of all, see this figure. Here in this figure, this is a conducting cylinder which is filled with a gas. Here is a piston of mass m, and here you can see the burner due to which the flames are being created, giving heat to this system. This gas is our system right now. This cylinder and the atmosphere nearby is the surrounding. One important point you should note here is that this piston is connected with a weight through a string and a frictionless pulley, right? Note that the mass of piston and mass of this weight is same. So here what happens, that this piston becomes in a way weightless, And due to this piston will not move due to its own weight, but it will move only when this gas inside pushes this piston outside, or the atmospheric gas pushes this piston inside. Alright. So here whatever work will be done by the system or on the system will be done by the gas and not by the weight of this piston. Here, when the piston is moving inside, it compresses the gas, it compresses the system. That means the work is done on the gas, on the system. Alright. If the gas is expanding and it is pushing the piston outside, then the work is done by the system. Alright. So I have shown here work in both the sides. The same way, if here heat is going inside, obviously in this case heat will travel inside, then it is said that heat is given to the system. Alright. But if the temperature of system is larger than the surrounding, then heat will travel outside. Then it is said that heat is given by the system. Alright. So I have shown heat Q in both the sides. Now, as you know, the total sum of molecular kinetic energies and molecular potential energy is known as internal energy U. Alright. Now let us understand how this internal energy will change according to work and the heat. See, if you do work on the system, internal energy of the system will increase. I repeat, doing work on the system increases internal energy. And the same way, if you give heat to the system, internal energy will increase. Means supplying heat to the system increases internal energy. So remember this thing, we can increase internal energy by giving heat to the system or by doing work on the system. Vice versa, if heat is given by the system to the surrounding, then internal energy will decrease. And the same way, if work is done by the system on the surrounding, then also internal energy will decrease. Right? Now here is an important note. A gas has certain amount of heat or a gas has certain amount of work are meaningless statements. Let me elaborate this. See, a gas can have internal energy or it can have mechanical energy, but it cannot have heat or it cannot have work, because heat is the internal energy transferred and work is the mechanical energy that is transferred, right? So system cannot have heat or it cannot have work. Yes, it can only have internal energy, it can only have mechanical energy. Okay. Now using the same figure, we are going to understand the first law of thermodynamics. Now let us see topic 12.5, first law of thermodynamics, a very important law in thermodynamics. Now to understand this law, first of all we have to take this figure in a reference. Here is the same figure, this is a conducting cylinder, here is the piston, and this is a gas as a system, and here is a burner which is giving some heat, and this piston is connected with a same mass of weight, so that the work will be done only by the gas and not due to the weight of the piston, right? Now for this figure we have to understand these physical quantities. Here delta Q is the heat supplied to the system. See, if the temperature of surrounding is more and the temperature of system is less, then obviously heat will travel from surrounding to system. So that is the heat supplied to the system. Let us say it is delta Q. Delta W is work done by the system. See, if the gas gets expanded, then it will push this piston outside. So that is the work done by the system on the piston, or say on the surrounding, right? I'm repeating. this will be the work done by the system on the piston or on the surrounding. So in that case the piston will go outside. So that work is taken positive and that is denoted by delta W. Here if the internal energy is increasing, then that increase in internal energy is taken as delta U. That delta U is positive. Now also note that when this delta Q and delta W becomes negative, see, if the heat is supplied by the system, here gas is the system, and if this gas is supplying heat to the surrounding, means if the heat is going outside, then delta Q is to be taken negative. Mind well, in this line and in this line there is a minor difference of to and by. If the heat is supplied to the system, then delta Q is positive. If the heat is supplied by the system, then delta Q is negative. The same way, if work is done on the system, suppose if the piston is compressing the gas, that means the piston is doing work on the system. So if work done is on the system, then delta W is to be taken negative. Means when this piston is coming inside, then delta W is to be taken negative. Here also between this line and this line there is a small difference of by and on. Work done by the system is positive, work done on the system is negative. Now because here heat, this internal energy and work, everything is sort of energy. So as per the conservation of energy we can understand that delta Q is the amount of energy taken, by which there are two things happening. One is that internal energy is being increased, and second is that this gas system is pushing this piston outside. That means this system is doing work on the surrounding. So both of these things, that means increase in internal energy and work done by the system, is happening due to the heat supplied to the system, right? So now we can write that as per conservation of energy, the heat supplied to the system partially goes to increase the internal energy and partially goes to do work on the surrounding. Work on the surrounding means work done by the system. And so we can say that this delta Q is equal to delta U plus delta W. Here this delta Q is equal to the sum of delta U and delta W. And that is known as the first law of thermodynamics. So delta Q is equal to delta U plus delta W is known as first law of thermodynamics. Mind well, as we already discussed earlier, when heat is supplied to the system, delta Q is taken positive. When the internal energy increases of the system, delta U is taken positive. And when the work is done by the system, or say work is done on the surrounding, delta W is taken negative. Here, if any of the case is opposite, then the particular value of that physical quantity has to be taken negative, right? So here delta Q will be equal to delta U plus delta W, means everything will be positive as it is shown in this figure. Now for the same cases we will see some special situations, and on that situation we will find out the result of the first law of thermodynamics, delta Q is equal to delta U plus delta W. The first case is isobaric process. Suppose somehow during the process the pressure of the system, that means pressure of the gas, is kept constant, means P is constant here. Now if the piston is moving outside, that means the inside pressure is more and the outside pressure is less, and due to that some force would be applied by the system on the piston. So the force applied on the piston is, let us say, F, and under this force, let us say the piston is traveling for a displacement of delta x. So obviously here the work will be equal to force into displacement, that is F into delta x. Now I am dividing this F by A. A is the area, cross sectional area of the piston, and I am multiplying this equation by A. So here I will get F upon A, which is pressure, and here is cross sectional area A and the displacement delta x. So that becomes the change of volume delta V. See, the cross sectional area of the piston is A and the displacement is delta x. So obviously the increase in volume will be delta V, and delta V will be equal to A delta x. So the work equation becomes delta W is equal to P delta V. You have to remember this equation. Whenever keeping the pressure constant, if the piston is traveling, if the piston is showing some displacement, then the work delta W will be equal to P delta V. Now come back to the equation of thermodynamics first law. So here you will get delta Q is equal to delta U plus delta W, but at the place of delta W we can write P delta V. So here is the equation when the process is isobaric. Now, if the process is isothermal, that means somehow during the process, let us say the temperature is kept constant. So here T is constant. Now when the temperature is constant, there is no change in the internal energy of gas. Mind well, if the temperature of the system, that means of the gas, remains constant, there is no change in the internal energy of this system. So when T is constant, delta U, that is the change of internal energy, will become 0. Thus the equation of thermodynamics first law will become delta Q is equal to delta W. That means here delta Q is the heat supplied to the system and delta W is the work done by the system on the surrounding. That means whatever heat you supply will be converted into doing work by the system on the surrounding. Now let us see isoqualic process. That means the volume remains constant. Now keeping the volume constant of the system, means of the gas, means that you are not allowing the piston to move. The piston is not moving, right? Then only V can be constant. If V is constant, then delta V will be 0, no change in the volume, and so there is no work done. When the piston is not allowed to move, how could you do some work? There will be no work at all. So delta W will be equal to 0, and from that we can say the equation of first law of thermodynamics can be now written as delta Q is equal to delta U. That means whatever heat you supply to the system will directly increase the internal energy of the system. There will be no work, only the internal energy will be increasing. The last one is adiabatic process. Now, adiabatic process is possible only if we put this container non-conducting. If the whole container, means the piston and the cylinder and everything is non-conducting, then only adiabatic process is possible. But when we put this system adiabatic, obviously no heat will be able to penetrate inside, or neither any heat will not be able to come outside. So in that case, delta Q will become 0. So here delta Q will be 0, but delta Q is delta U plus delta W as per the first law of thermodynamics. So that also will be 0. And so we can write delta W will be equal to minus delta U. I repeat, delta W is equal to minus delta U. Now delta W means the work done by the system on the surrounding, right? When you take delta W to be positive, that means it is a work done by the system on the surrounding, and that will be equal to minus delta U. That means it will decrease the internal energy. Thus, work done by the system will decrease the internal energy with the same amount. And vice versa, if you take this equation as delta U is equal to minus delta W, I repeat, delta U is equal to minus delta W, that means, see, when you take minus delta W, that means it is work done on the system. The piston is coming inside. So it is work done on the system, and that will give you plus delta U. That means the internal energy is increasing. So if we do work on the system, then it will increase the internal energy with the same amount. Alright. So dear students, today we have learned topic 12.4, that is about heat, internal energy and work, as well as topic 12.5, that is about the first law of thermodynamics and its different cases. I hope that you enjoyed these topics, and I recommend that all of you please note down all of these equations, because these are very important equations for all of these different cases. Alright. So as of now, I am winding up this lecture today. Signing off, Anshul Baldania.